Recording is on. I'm spotlighted. Okay, hello everyone, welcome to my talk. I'm already sorry if I messed something up. This presentation has a lot of moving parts, screen sharing, audio sharing, presentation, everything can go wrong, so fair warnings up ahead. So my talk is about sound synthesis and how you can do it in practice on the web, just using your browser and possibly an IDE. The presentation is going to be two parts. The first part, probably the first 20 minutes, is going to be some theoretical basics about audio and synthesis. And then the second part is going to be live coding and coding example and stuff that you can hear. And if you already know about synthesis, then you can skip the first 20 minutes. If you are going to be present for the second part and you want to hear what we are doing or what I'm doing, please try to find a pair of headphones because it's going to be like a stereo effect, and most of the sounds that you can hear can only really be heard with headphones and not through the speakers, but maybe MacBooks are quite good for that. So enough talking, I'll jump into it. So if we want to talk about synthesis, we have to talk a little bit at least about acoustics. Acoustics is the study of sound. The physics aspect of it is acoustics. It's how waves are traveling in different means and mediums. For example, how sound or air compression is traveling through air. Sound is basically waves, and acoustics is the study of waves. Psychoacoustics is the psychological study, basically the corresponding side of how we perceive sound. It is very much a big component of how we hear and what we constitute as audio, or what we conceptualize as audio. So that is also a very big aspect, and I will try to focus on both of the sides as we go forward. Sound is basically just air compression waves. It is air molecules compressed to a different level at different ranges in the air, and these traveling waves are hitting your eardrums and you're perceiving sound, and your brain is giving you the feeling of hearing. One more thing I want to highlight, we will go into some technical speak as well, and I will be using some of these words. So I want to clarify the terminology. Pitch, as we refer to, pitch is how high a sound is. So highly pitched sounds are very high in tone, low pitched sounds are very deep or rumbly sounds. This is the psychoacoustic aspect. The physical aspect is how fast the object that's giving off that sound is oscillating. So all of the sounds are coming from oscillating objects. Very often it is your speaker, but whatever else physical objects you can hear, a guitar or something, that is always coming from some sort of oscillation. And how fast this oscillation is the pitch of that sound source or that sound. Amplitude is how densely compressed the air is at certain points. This is what we perceive as loudness. So the amplitude of how big the waves are corresponds to loudness as you perceive it. And timbre or timbre is how this compression pattern changes over time. So oscillations in the air are not super clear. It's not like, gradually getting more compressed and then less compressed, but there is a lot of change in behavior. We'll see a lot more of this later visualized. That is basically the sound character of how you perceive a sound. Humans can tell apart guitar sounds from glass clinking, from drum sounds, from everything. Your brain is used to it, and your brain is very much capable of perceiving this timbre. And it is very good that we can do analysis on sounds in a visual format, because also our brains are very good at understanding visual cues. And this will help us a lot in understanding what we are hearing. So to say, you can see sound through these analysis lens. And usually we have two aspects of analyzing sound. One of them is the time domain representation. This might be more familiar for yourself when you see something like a sound wave in any context. This is what you're usually seeing. It is the amplitude of that sound graphed out over time to the right. So these waves going up and down means that the amplitude is higher at certain times and then going low. And this one is also that. The other lens or the other aspect, which is not really competing, but it's a very different, it's a sideways view on sound, is the frequency domain representation. In this representation, what we're graphing out is at certain frequencies, at certain oscillation frequencies, how loud is that sound? Because ultimately we'll see that any of the sounds that we're hearing that is not a pure sine wave are comprised of a lot of sine waves added together at different frequencies and different amplitudes. And that will give some more interesting sound than just the straight up beat that you get from a sine wave. Let me show you a few examples to get this a bit more visualized. This super ugly UI is created by me, and you'll see more of this later on. So what you can see in here is that we are visualizing a sawtooth wave at a frequency of 1,000 something. And this is not super interesting, the rest. What you see in here, this is the time domain representation. You can see a lot of waves, very spiky waves visualized over time. With yellow, I'm marking how you can read the pitch of an oscillation or a sound, how densely compressed these waves are compared to this. This is a super low pitch oscillation. You can see in here it's only 52 hertz, which is 52 oscillations every second. This one is more than 1,000 oscillations per second. So that is yellow for the pitch. Timbre, the sound character, is how these waves are looking, how you can see them, which means what is the character of these sound waves. And in the sawtooth waves, what you can see is very spiky waves. So the change from high compression in the air to low compression in the air is it's a very much sudden drop. We'll see different waves later on. And amplitude is how tall this graph is how loud is the sound altogether. Again, you can see a lower pitched wave screenshotted in here. And this is the frequency domain view. In this image, what you can see is the low frequencies are represented at somewhat higher amplitudes. And as you go for higher frequencies, you get lower and lower content. Most of the interesting waves are added together from a lot of sine waves, and we call these harmonics. So here, more or less, here is the base frequency for 200 hertz, and all of these subsequent frequencies that are represented at very different and gradually lower amplitudes are called harmonics. This will come in handy later. So much about acoustics. Let me jump to a bit of a history about synthesizing and synthesizers. I'm not really going to show you this, the history lesson. If you are interested, you can check out historyofsynths.com. It's pretty cool. But what I want to highlight is just to place it in the grander scheme of things. I think it was around 1964 when one of the most commercially successful synths of the time came out by the Moog company run by Robert Moog. And this was, I think, the advent of the modern synthesizers as we think about them. Those synths were huge, unwieldy, but they could already generate a lot of very nice sounds. And soon after that, there was a whole revolution in synthesizer making. A lot of brands came in, and as we stand right now, currently you can get very good synthesizers for a few $100s, or you can do it for free in your browser. One more thing I want to highlight about synthesis and synthesizers is that the hardware versus software aspect. I think it's interesting to understand that we came from a hardware world, meaning that the synthesizers of the 70s and 60s and mostly around the 80s as well were hardware synthesizers. Hardware synthesizers mean that there is an analog circuitry, which means that there is a voltage level or currency level running through this electrical circuit board, and all of the components that are shaping your sound or creating some interesting aspects of your sound are implemented as physical chips and resistance in the circuitry. So it is very much physically present. And this gives it so-called warmth, because analog world and physical world is not perfect. So you'll have a lot of residual electricity here and there in the circuit board, and that will give it some unpredictability, imprecision, but this is giving it its so-called warmth. And then later on, we came to a world where our computers were smart enough and strong enough to compute and model everything digitally. So what we did is we basically replaced the analog circuitry with mathematical computations on data. So in the software world and the digital world, what you do is you basically have data flows and functions as components, and you transform your data flows so that you can get infinitely precise and infinitely creative solutions with your sound. And we're going to be taking a look at some software synthesis. Whew. Okay, so just to recap, sound waves are air compression. The key terminology is pitch for how high is the sound, amplitude is how loud is the sound, timbre is the sound character. The human hearing is from 20 hertz, super low voice, 20 oscillations per second, up to 20,000, super high, I think. Way too old to even perceive 20,000 hertz, but that is top of the theoretical human hearing range. And subtractive synthesis is the methodology that we're going to take a look at. I'm going to jump to that immediately. Subtractive synthesis is one of the modes of synthesis. So you can imagine that there's a lot of ways to create sound. There's a lot of ways to somehow create an oscillating wave and then modify it. One of the ways is called subtractive synthesis. And this is probably one of the most prominent ones out in the market right now. And this is one of the easiest ones to understand, I think, because the components are not super difficult to comprehend. The basic of this sort of synthesis is that you start with a sound that's harmonically rich. So you start with a lot of frequencies, a lot of different frequencies in the frequency domain. And then you take away, or you sculpt away, some parts of the harmonics, and then you sculpt away some parts of the sound over time. So you modulate the sound, and you change the harmonics content, and that's how you can get interesting sounds with an interesting behavior over time. Let's jump to the components. So these are the components for subtractive synthesis. These are going to be more or less the same anywhere you look in the subtractive market. Oscillators are the basis of subtractive synthesis. This means that you have something that oscillates at a set frequency or in a changing frequency range. This is generating the sound. As I said, sound is basically oscillation. So you start with this. Oscillators can usually generate lots of different wave formats. So sine wave is the most clean one. You might be familiar from your dial tone from your phone. Square wave, sawtooth, and triangle are quite interesting because they're harmonically rich. These are the ones that we can mostly use in subtractive synthesis. And if I want to give you like a biological parallel, then I would say vocal cords is the oscillator of the human voice, because this is where all the sounds are made. So your bass sounds are coming from the vocal cords. The next component is the filter. As I said, subtractive synthesis is about removing harmonic content, and the filters are the components that can remove harmonic content. We will see it later. It's going to be very well visualized that as you play around with the filters, you can remove different parts of the frequency domain. So you can remove low frequency or high frequency, and this will quite interestingly change the character of the sound. And if you want to get, again, a human parallel, this is your mouth and your throat. So the fact that my mouth is moving, it is changing the harmonic content of my voice, and that is what's giving the human speech its character. Amplifiers are quite easy. Amplifiers can be used to amplify a signal or damp a signal or dampen a signal. We'll see why this is good later on. And the human parallel is the lungs. So with higher output pressure from your lungs, you are becoming louder. Lower output is less loud or quieter. Envelope generators are components that are signal shapers or signal generators. Again, as I said, like in the world of synthesis, we're talking about signals running through currency or the systems, and these signals can be used to modulate or drive other components. So An envelope generator by itself is not very useful because it's just generating some signal and you can really not hear that thing. But if you combine it with an amplifier, then you can use a signal that's running up, so gradually becoming more loud, and then running down, so becoming quieter over time. This will give you like the sound pulse, as if you just hit one key on the piano instead of a constantly beeping noise. If you combine an envelope generator with a filter, then you can get some interesting effects, so-called wub effects that you can use in electronic dance music very well. And envelope generators can also be used to drive oscillators, so you can create sounds that are changing in pitch over time, and this can be used to simulate drum hits, and we'll see this later on. LFOs are also oscillators. LFO is an interesting component. It is a low frequency oscillator, so it's basically a signal that is very slowly changing. And if you route this into, let's say, a filter, then you can build tension and remove tension gradually. A good parallel that I like to use for an LFO is your body running up to your hi-fi and then just slowly turning one of the knobs that they will find to keep the music interesting. Or another parallel could be if you drive an LFO into an amplifier, a VCA, then that will over time change the loudness of a certain voice. In the guitar, when people are playing around with the strings after they have hit the string and they just play around with it, they can get this tremolo effect, and that is considered an LFO. There's a bunch of other controls in systems like this, but we're not really going to be talking about these. But these are mostly for driving some of the parameters. So let's say the pitch of a certain oscillator can be controlled by a keyboard, so you can play distinct notes from the piano, or sequencers so that these notes can be automatically played. The good thing about software synthesis is that you can just code whatever you feel like. So if you feel like coding a device that is hitting the same note super fast, then you can code it. It's really up to you to program anything. And effects are also super great. They will give some more interesting character to sounds, but we'll not really have time to cover those. So these are the components. Again, oscillators create sounds, filters remove harmonic content, amplifiers make something loud or quiet, and envelopes and LFOs can drive other components with signal generation. Okay, this was the theoretical part. I think I have a few more minutes left. Let me show you the hello world for the Web Audio API. And for that, I'll have to share sound. Someone please speak up if this is not working well. Hang on. Share. Actually, I will share sound and screen so you can see what I'm doing. All right. So this is the hello world example for the Web Audio API. What you need to see in here is that everything is always happening within an audio context. So audio context will give you all the tools and all the components for subtractive synthesis. We create an oscillator within that context. We create an amplifier and a filter within that context. We set up some parameters for these. So we set like a middle A, we set it to be sawtooth. We make it a bit quieter so that you guys don't go deaf over the initial sound. We set some filtering frequency, and we connect all of these together. So I forgot to mention this very interesting part is that the Web Audio API is implemented as a graph. So you'll basically have nodes, graph nodes that are connected by edges. This is the modeling in software for wires. So imagine that I take an oscillator that gives a bass sound. I connect it through a wire into an amplifier that will reduce its loudness. And then I connect it to a filter so I can change its character. And then I connect this output from the filter into the audio context destination, which is my sound card, which is either my headphones or in this case, probably sharing through Zoom. So I just bluntly copy this to a super empty page. Nothing else was set up before. Nothing is happening. It's because I haven't started my oscillator. And when I say oscillator start, someone say a thumbs up if you can hear this. Okay, Yvette can hear it. So this is my oscillator going on. I can change its frequency. and then the sound will change. So this is what's happening. I will not go deeper into this example, but you can imagine that everything in this audio graph can be parameterized with a lot of different parameters, and you can change all of these. And in the coming examples, what I'm going to do is show you an example project that I created with a bunch of steps, just showing more and more from the audio API. I also did build some very basic editor next to the control panel, so I can show you the code that's more or less doing this. And I'm already sorry if something is not really understandable. I will not take a very in-depth look to the code. I just wanted to show you a few features. So starting out from the very, very basics, we have a bunch of different wave shapes. So this is how a sine wave sounds with changing frequencies. This is how a sawtooth. Okay, I actually have a better idea. One of the other examples, the second example, still has the waves, and also it has some gain control, so I can make it a bit more quiet. So let's see. Okay, sweet. So this is a sawtooth, and it's more interesting when it's lower. This is more or less our hearing range. This is already like crackling because it's so slow that you can hear the individual hits on the oscillator. As you change the cutoff frequency, the character is supposed to change. You can hear that we are removing the upper harmonic content and only leaving the lower end. Also, this is how a square wave sounds like. Okay, very much like the other ones. Okay, any comments or too loud, too quiet? Okay, fine. I will proceed and let me know if something is too loud or quiet. So for the code, what you can see in here is there's no cheating. Again, I'm creating an audio context, creating, again, the standard elements, an oscillator, an amplifier, we usually call this a gain node, and the filter. And then I just connect them together like puzzle pieces. And this is some visual, like very basic interaction that I set up in here so I can control these parameters, but they will ultimately just go into different parameters of my nodes. Okay, and when I run this, when I start it, you'll start to hear the sound. Let me go to the most interesting example so far, and they're just going to get gradually more and more interesting, is when we start visualizing the sound. So let me run this and set a low gain. Now we can visually see with one of the analysis modes, this is the time domain analysis, yes, the time domain. And I'm sorry, because of Zoom, I don't see much here. So this is how a sine wave looks. And what you can see is it's not quite there, but I'm sure that we can find a frequency at which it's stabilizing more or less. No. What I'm looking for is a frequency that is more or less there with my refresh rate. There you go. So it almost looks like the wave is still. I don't see any feedback now because my Zoom is quite small. I don't even know how to go back. Anyway, someone speak up if it doesn't make any sense. But what you can see now is is a sine wave that is at the frequency that's very close to the refresh rate of this visual component that's doing the analysis. So it more or less looks like it's still. This is why this is called a saw wave, because it looks like a sawtooth. And as I change the cutoff frequency, the wave shape changes as well. And slowly it goes into a sine wave. Same goes for square waves. This is originally a square, but then it turns into a sine wave. And then if I were to crank up the loudness, the amplitude would increase. So I think this view is not super interesting. What is more interesting is this view. This is the frequency domain. Again, what you see is a bunch of different sine waves adding up to create this square wave sound. And as I increase the cutoff frequency, you can see that a bunch of the harmonics are reappearing. So the filter is cutting off these harmonics. If I change a different type of filter, I only leave in the frequencies, then I can cut off the lower frequencies. There's a bunch of different filter types. For example, bandpass is only leaving in a band of frequencies. And these all sound quite different to the human ear. Let's stick to the low pass. This is the most commonly used. One more thing I want to show you in here is that if we're going to higher frequencies, you can see that there's only a few of these frequencies that are staying here. And then when I switch to a sine wave, you basically hear the same thing. This is more or less the same. So at very high frequencies, it's really hard to tell apart sounds, but lower frequencies have very different audible properties, as well as the frequency content is much more interesting. So your filtering can do a lot more to sounds that are harmonically rich, and thus this is mostly working in lower frequencies. So enough blabber about this. Let's move to the next example. I'm going to show you how we can program some of these components. Again, trying to hide Zoom. So the code in here is going to be showcasing how we can, I did a few shortcuts, again, same components, oscillator, filter, amplitude control, and then I created something for envelope generator. This is, as I mentioned earlier, is used for emulating signal levels that are running up and then gradually dissipating. And this is to model sound waves or sound pulses. And for that, we can control the gain of an envelope generator, which is basically the same thing as an amplifier. So we will dampen or amplify the sound, and this will over time give us like a sound pulse effect. The API allows you to ask for some sort of linear progression over time. And then what we're setting up in here is that in 0.1 seconds, it should hit maximum value. And then after that, in 0.1 second, I think I said 0.1, but 0.01, very fast attack and very slow decay, or fairly slow decay. With this, we get a beep sound. Now, this is not super interesting in this view because envelope generators are operating on time. So let's look at it from the time perspective. You can see that the sound wave is appearing and then disappearing. With even lower release time or decay time, you can see that it starts high and then runs out. It's not super interesting. It's the same thing with all of the waves at this point. Okay, so now I can simulate I'm hitting a note on a keyboard or a piano or something, because this is now not a constant beeping noise, but this has some properties that are closer to physical reality, that it's changing over time. So let's see what we can do. What we could do also is that I create a function in JavaScript that will hide away all of this setup that I need to always control. What is the attack time and what is the decay, and wrap it up in a function. And then let's just call it trigger envelope and try to use this in my code. So I will trigger an envelope on any audio parameter with certain attack time and then certain release time. So let's try to model the same thing that we did here. I will want to trigger my envelope generator over 0.1 seconds and dissipate over 1 second. So it's going to be a slowly dissipating sound. Oh, something happened. The parameter. Bad news. As usual, coding errors. Your param is the envelope generator. Oh yeah, we wanted to change the gain. 0.1. Okay, we're there again. Now it just looks smoother. So I can also automate this. I could say set interval, and this is JavaScript from now on. So you can let your fantasy go wild and try to imagine how you would do this nicely. But let's say every 500 milliseconds, I will hit one of these nodes. This is like a turn signal. I could also go ahead and, I don't know, create a function that will run on a pattern. Now I'm just making it up, where I say, okay, hit it with 500 hertz and hit it with 300 hertz. And then just repeat this every 40 milliseconds. There you go. And then do it for the, I don't know, the envelope generator. So this would be something like a very stupid pattern generator that I hit 500 hertz and then 300 and 500 and 300. Again, you can just code whatever you want. I didn't really go super deep at this example in implementing nice, neat features for sequencing, but you can imagine that with programming, you can do anything in here. Let me move to the next example. This was highlighting how you can sequence stuff, how you can automate shape changes in sound over time with this, what was the API? With this set value and linear ramp to value, because this is linearly going to a set value. In this second example, I'm trying to showcase how you can do something very musical. So going for notes that you already know from music class. And for that, I created something very convoluted, like a very convoluted audio device, because I also want to show you that you don't always, you can do more complex things than just a simple sine wave or a sawtooth. So for this example, I created two oscillators, set up different parameters for them, and both of the oscillators will go into the same filter node. No, hang on, two different envelope generators. And then these will go to the same filter node. And then we run it through a reverb effect, so we can get it some juicy effects. And then we run it through the analyzer, and then finally connect all the output to the destination. All this is to say that we will have now two oscillators going at the same time, so you will hear something more complex. This is a bit nicer. This is a lot more interesting, I would say. And since we have two oscillators, and we can change the panning, so how do you hear what, which stereo side you hear the sounds on. We can play with this too. We can also change very small detuning. And you can see how these small, small spikes are moving compared to each other as I detune the oscillators compared to each other. Okay. What I wanted to showcase with this again is that you can create more complex harmonically more complex audio devices just by stacking more and more oscillators on top of each other. These behave a lot more interesting. And what you can also do in code is to create event handlers so that you pick up keyboard hits. So this is again very basic. As you can see, on every keyboard hit, I will translate the key that I hit into some set frequencies. I try to devise a method to find some frequencies that are resemblant to the musical notes that we know from music class. And then you can now play this device as a piano. So now I can play almost like a synthesizer in my browser. I also have a bit of different code. Instead of driving both of the oscillators with the same incoming notes, I will instead do a keyboard split. So whenever I hit some upper parts of my keyboard, I will change one of the oscillators and I change the other oscillator with the other part of my keyboard. All this is to say I can play more notes at the same time. So let's hope that this will work. It's just all filtered. Sorry if I gave someone ear cancer. I hope this is not too bad to tolerate. And we can crank up the juiciness with some reverb. Okay, I'm not a keyboard player, and especially not like a physical laptop keyboard. So let me jump to the next example. What I wanted to show with this is that if you're changing your oscillators to certain frequencies, then you can be very musical with it and you can actually play sounds nicely. And I think I have a few more minutes left, right? Like 4 minutes. So I will jump to my last machine and I have to transform to a beat maker for that. So I created a beat machine, which is a lot of code creating a lot of these two oscillator devices. So 1 synth, 2 synth, and all these are the same parameters that I used the other time, like what should be the oscillators and how wet the reverb should be and where should we filter and how fast or slow individual sound hits should be. I also created drums. As I said, if you change the frequency over time, then you can emulate the behavior of drums. I can create snare drums as well, magyarul pergődob. We can create hi-hats, szintányér, so that we can have a whole repertoire of musical devices set up together. And if I start this with no sound at first, let's hope. Hang on. So this is the, okay. Okay, now you can hear the kick drums. Adding the snare drums, adding funky, adding some hi-hats. Can you guys hear it? Okay, I'm not seeing nodding heads. I can barely see anything in these glasses. But the point in here is that combining all of these devices together, you can get very musical because you can virtually simulate all of the behaviors. And then the point is, this is all running on my computer. I think like even a lower end computer would be able to do it because your browser gives access to the low level APIs to drive all of these synthesizers in your browser. So if you get super creative and you do like I did, create very complex devices that are emulating drums, emulating hi-hats, and then you connect all this big graph of nodes together into a single output and create sequencers for yourself. Then you can prescribe all sorts of patterns for your drums, patterns for your melodies, and you can go and get creative with music. So let me show you some more patterns that you could do. Let's try this one. I know the reason why this is quite shitty is because I have to control everything with a touchpad on these very basic inputs. But you can imagine how someone would go the extra mile and create nice creative controls for this. So you can use whatever you have at hand. So I will share the code. Whoever is interested can tweak around with it. There is a few utilities that I created for hiding away sequencers, for hiding away hitting distinct notes that you already know from music. And you can play around with it, run your code and hear what you're getting. And it's also good for analyzing in the frequency domain. So what I also wanted to show, hang on. Last thing is this frequency analyzer is working for whatever devices we plugged into here. So if I just show you what the drums are doing, just the kick drum alone is playing low tones, very low pitch. Snare drum adds some energy and some noise in all of the frequency range. And the hi-hat is really only working as a noise source. And then if you filter out hi-hats, they get a bit different character. And then the game in here is to just keep all of the frequency domain busy with everything unless you want something boring. Thank you so much. I will stop sharing, or I will just open up for questions for now. Mm-hmm. Any questions? No questions? Any requests? Any music that you like, and I can try to reproduce it?
You should do the elevator music part between the talks from now on.
I could have tried that. I could have really tried that. It would have been interesting. Unfortunately, I only know how to do dance music because that's quite easy. Just constantly hitting drums and some melodies.
Just do that.
Okay. Right. I will send in the code if anyone wants to play around with it. Otherwise, thank you for listening. Stopped.